Hey everyone, today I want to kick off our final unit on global change, Unit 9 on global change. And this is basically all about how do the choices that we make as individuals, as populations, communities, but also as a species impact the world around us on a global, very large scale, the entire Earth. How is my actions impacting someone on the other side of the globe? And also, that's going to tie into the topic we talked about in Unit 5, the tragedy of the commons. The Earth is a shared resource. And every action that you make is going to impact that shared resource for everybody in the rest of the world. So the first example of global change, the first topic is the ozone layer. You may have heard of the hole in the ozone layer, and we've talked about the ozone layer when we learned about air pollution. The ozone layer is located in the stratosphere, uh, and there is currently a hole over the Antarctica, more or less, the hole in that ozone layer. You might recall that ozone in the troposphere is bad, it's air pollution, but ozone in the stratosphere contributes to the ozone layer, which helps block ultraviolet rays from the sun from reaching Earth's surface and reaching us. That's good. We like ozone that's in the stratosphere because it protects us from UV rays. Uh, UV rays can lead to increases in skin cancer. It can lead to cataracts in your eyes. It can also disrupt uh, the development of various organisms and various ecosystems. But two big ones, at least for humans, are skin cancer and cataracts. But the ozone helps block that. So we like ozone in the stratosphere. But humans are having some serious impacts on the ozone layer. If you look back into the 1980s, hairspray was a big deal back then, and believe it or not, that shows in the ozone layer. So the ozone layer in the stratosphere, that ozone can actually get broken down by these chemicals called CFCs, or chlorofluorocarbons. And these are molecules that basically what they have is it's a carbon with some fluorides, these are the orange, and a chlorine atom. The fluoride is the white, carbon is the black, the chlorine is the orange. And the chlorine will dissociate from the chlorofluorocarbon, and it will chemically react with the ozone molecule, rip off one of the oxygens, and basically convert ozone into oxygen. So it destroys ozone. And these CFCs are found in a variety of chemical products, including aerosols, coolants that are used in refrigerators and air conditioners. One of the chemicals you may recognize is called Freon, which was made by DuPont, a chemical manufacturer. These CFCs have very, very high residence times. That should say residence, not resonance. Whoops. They have high residence times, meaning they stay in the atmosphere for a very long time. They don't break down very easily or quickly. And ultimately, what they do is they turn that ozone into oxygen. So these CFCs were being released very frequently, especially in the 1980s with all that hairspray. Partially joking, partially serious there. And you can see if you look at these images that the hole in the ozone layer, the bluer or the more purple the color, the less concentration of ozone there is. The hole in the ozone layer at the South Pole is starting to get larger and larger as we enter into the early 90s. Why is it forming over the South Pole, you might wonder? Well, it's very, very cold there, and there's a special type of cloud called a nacreous cloud, or a mother of pearl clouds, pictured here, that form under very, very cold conditions. So they only form in the winter of the Antarctic, and those clouds are like the ideal chemical surface for this reaction to occur, for the CFC to release the chlorine and react with the ozone. That's kind of besides the point. These CFCs come from a lot of different chemicals, but the main one that we want to be worried about are these CFCs here in the sort of gold color and the blue color. And those we actually were able to reduce significantly. So the chlorine that is reacting with the ozone was the big problem. And as you can see from this graph, most of that chlorine is coming from these types of CFCs here. So why don't we just get rid of CFCs? And that's what the Montreal Protocol did in 1987. It's an international treaty signed by a multitude of countries to phase out CFCs and replace them with other chemicals, in many cases hydrofluorocarbons, which are not contributors towards ozone depletion, although they are greenhouse gases. It's one of the most successful international treaties of all time. You can see if you look at this graph, the trend was an increasing number of CFCs and sources of stratospheric chlorine. And with the Montreal Protocol in the late 80s, it actually led to a significant dip, and we've actually seen a big recovery in the ozone hole since then. The ozone hole was the smallest it's ever been since it was first recorded in the early 80s in 2019. So that's great news. That means the Montreal Protocol is working. Here's another graph showing the ozone concentration in the atmosphere. You can see that in the 60s and the 70s, it was pretty high. And as we entered the 90s, it started to really dip due to all those CFCs. But after the Montreal Protocol was enacted, it actually started to recover a little bit and is still on the upwards trajectory since then. This is a great example of how legislation, particularly international legislation that works with the military, with the economy, with businesses, and with the people, can have a huge impact on an environmental problem. Granted, it is more targeted. We had to target CFCs, and that eliminates most of the issue. But it does illustrate that if we work together, we can accomplish some serious, significant goals. The second example I want to talk about is global climate change. This one is, first of all, it's not connected to the ozone layer. There are two separate things. The hole in the ozone layer and climate change are not the same thing, which is why I've separated them here. But global climate change is connected to much of the global issues that we see environmentally around the world today. First of all, global climate change is just a large-scale change of Earth's long-term weather patterns. You might remember that long-term weather is climate. The increase in carbon dioxide is at the core of this issue. It is anthropogenically caused, meaning that there are more sources of CO2 in the world because of human activity, burning fossil fuels. And ultimately, that increased CO2 can lead to increased temperature, it can lead to increased sea level, and it can actually increase the acidity of the ocean as well. But in order to understand climate change, we first need to understand the greenhouse effect, which is pretty pivotal to understanding how climate change can even come about in the first place. So, excuse me, let's imagine a scenario under normal conditions with the greenhouse effect. You've got Earth in green, the atmosphere is this blue layer above, and space with the sun in it. Normally what happens is that solar radiation from the sun comes down, penetrates the atmosphere, hits Earth. Earth absorbs a lot of that heat and then emits a lot of that heat as infrared radiation. And you might notice that most of that heat, most of that radiation leaves the atmosphere and goes back out into space. Some of it does hit the atmosphere and bounce back towards the Earth and stay within the atmosphere, stay on the Earth's surface, keeping the Earth warm. That's a good thing. Without the greenhouse effect, the Earth's surface would be 0 degrees Celsius, be freezing cold. But the greenhouse effect helps trap some of this heat in the atmosphere because of greenhouse gases that are in the atmosphere, like carbon dioxide and methane, etc. They can hold that heat really well and prevent it from escaping the atmosphere. And that keeps the Earth's surface and the atmosphere at a slightly warmer temperature than they would otherwise be. And you can see the atmosphere warms here. Now, there are a variety of greenhouse gases, and they have what is called a global warming potential, a GWP. The one we talked about the most is CO2. And that is the baseline global warming potential. And that number, that index, basically just tells us what is this chemical or this molecule's ability to trap and absorb heat in the atmosphere. So the higher the number, the better it is at trapping heat. So CO2 we use as a baseline. We say that's got a global warming potential of 1. Over the span of 20 years or 100 years, it will have a potential of 1. If you look at something like methane over the course of 20 years, it can be 80 to 90 times more effective at trapping heat than CO2. Now that goes down over time as methane starts to decrease in concentration, but it's still much higher than CO2. Nitrous oxide, even more high, and CFCs are the highest of them all. Thankfully, we phased those out due to the Montreal Protocol. Something to keep in mind, water is a greenhouse gas, but because it has such a low residence time, it doesn't contribute to global change. And also, you might be wondering, well, why do we care so much about CO2? The numbers are so low compared to these other molecules. Well, the reason for that is because the amount of CO2 we're putting into the air is much higher than the amount of methane or nitrous oxide we're putting into the air. we're putting so much CO2 in the atmosphere that it's actually having a pretty big impact despite its low global warming potential. Not to mention that it has a very high residence time, meaning it hangs around in the atmosphere for a while. So what happens when there's too much greenhouse gases in the atmosphere? I just showed you here, this is normal conditions. We have some greenhouse gases and they help keep the atmosphere warm enough for us to survive. But if there are too many greenhouse gases, what's going to happen? Well, same thing at the start anyway. Solar radiation will come down from the sun, the earth will absorb some of that radiation and it will absorb that radiation out. But this time, there's so many greenhouse gases in the atmosphere that very little of that infrared radiation can escape, and most of it gets trapped and reflected back into the atmosphere and back into the Earth's surface. So the atmosphere gets way, 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 way warmer than under normal conditions. So increased greenhouse gases lead to increased heat trapped in the atmosphere. And if you couldn't, to put it into words in the most simplest form I can, some gases trap heat in the troposphere, in the atmosphere, and too much of those gases is going to cause the Earth to overheat, right? If you have too many blankets on, you're going to get too hot. It's that simple, right? The gases are like the blankets, and the heat is the Earth's heat that it's releasing. The infrared radiation is a lot like your body heat. Here's another diagram showing that the greenhouse effect traps heat inside the Earth's atmosphere, and it also says a little bit about, hey, without the greenhouse effect, we would be freezing cold. The issue is not that the greenhouse effect is bad. The issue is that the greenhouse effect is sort of steamrolling over everything else and snowballing because we've put so many greenhouse gases in there that the greenhouse effect is almost too extreme for us to survive. And that's going to lead to intense global warming. How does that connect to climate change? Well, climate change is caused by increased temperature due to CO2, right? That all that temperature that is, or all that heat that is building up inside the Earth's atmosphere and leading to increased temperature is going to lead to global climate change. And those greenhouse gases, especially CO2, are increasing due to human activity. So at the end of the day, climate change is an increase in CO2 due to human activity, which then leads to an increase in global temperatures. Here's a graph illustrating the concentration of CO2. This is called the Mauna Loa curve because it was taken at a Mauna Loa observatory in Hawaii. You can see the concentration of CO2 goes up with time. The red line represents annual fluctuations due to photosynthetic activity, but the general trend is up, going way up. Every year continues to go up, more carbon dioxide, which means that we're going to have higher temperatures every year because carbon dioxide traps that heat. And so there are I'm talking hundreds of thousands of years in the past, so geologic time, there are fluctuations in Earth's levels of CO2 and Earth's levels of temperature, but nothing like what we've seen today, right? We have seen major global shifts in temperature, but today, those shifts are much different. Look at the time point, 0, that's where we are now, or I guess this graph's a little bit old, 1994, but you can see the general trend is shooting way up compared to some of these previous trends that we've had. But this graph also does a nice job of showing how that as CO2 concentration goes up, the temperature will also go up. Excuse me. So why is increased temperature a problem? This should be pretty straightforward, but let me give you some of the many reasons why increased temperature is a problem. First of all, it's going to lead to that large-scale global climate change. What does that look like? Well, you might melt permafrost, which is permanently frozen soil in high and low latitude areas near the poles. Methane is often trapped in that soil as a gas, but because it's frozen, it's trapped in the soil. If you start melting that permafrost, methane is going to get released, which is only going to exacerbate climate change. Additionally, you're going to lead to melting of the ice caps. That's going to put a lot of fresh water into the ocean. It's going to lead to sea levels rising. It's going to change the ocean currents because you've got now a lot of cold water and it's fresh water. It's not salty. That's going to disrupt the ocean currents because the ocean currents depend on the salinity and the temperature. It's going to lower Earth's albedo, which I'll talk about more in a couple of minutes, and it's going to displace any populations of people, cities, but also ecosystems that are on the coast. As the sea level starts to rise, they're going to have to migrate inland. Additionally, going hand in hand with that, As the temperature increases, the range of various species where they can live is going to change, and that's also going to change where diseases are most commonly found, which we talked about in my last video. It can impact wind currents. Think back to Hadley cells, learning about the Hadley cell, which is a giant convection current, right? And that depends on hot air rising and cool air sinking. Well, if you've got major temperature changes, that's going to alter those Hadley cells, those polar cells, those ferrule cells, and might lead to changes in global wind patterns. You also might see changes in soil fertility and viability for plants to grow in, because as the temperature increases, moisture decreases. It might make the soil a lot more prone to erosion, but also a lot less fit for plants to grow in. And of course, the most bluntly, if the temperature gets too high, organisms, humans, animals, plants can die due to exposure to high heat and drought. Drought's another example, right? Increased evaporation leads to loss of water. You also might see mass migration as people move away from the coast and inland. In the United States, we've got a lot of land, it's okay, but in smaller countries or island nations, they're going to start to see a lot of people leaving those areas and moving elsewhere. We're starting to see that in Bangladesh already, which is a coastal nation, not an island nation, but it is very low in terms of its sea level. I want to talk a little bit about this positive feedback loop that we talked about on the second day of school, which has to do with Arctic ice. If you remember, ice is white, or snow is white, and that's going to reflect a lot of solar radiation. It's got a high albedo, same reason you wear a white t-shirt when you go out on a boat or in the hot sun. It's going to reflect that heat. But as the temperature increases due to global warming and climate change, that ice is going to melt, which means that there's less solar radiation that is reflected back into space, and more is being absorbed by the Earth, which means that the Earth is warming at a faster rate, particularly at the polar regions, which ultimately means that those ice is going to melt faster. And it leads to this vicious cycle, this positive feedback loop, where as the temperature increases, you have less sea ice, which means you have a lower albedo, which means that more heat is getting absorbed, which means that the temperature is getting hotter and there's less sea ice, and it just keeps going and going and going. That's a great example of a positive feedback loop and something you should be familiar with. Fortunately, there's a lot we can do about climate change, and it's very much in the media and on people's minds, so there's a lot of attention towards it. There's a lot of legislation being thrown out there. The Kyoto protocols from the 80s, not super successful, but on the table now are the Paris Climate Accords and the Green New Deal, which, if they can gain some more traction, especially with the United States, can make a significant impact. But doing what you can, participating in a climate march or a climate protest, voting, spreading the word, educating your friends, your family members, etc., that can have a much bigger impact than you realize, because once everybody is educated and understands the significance of the situation, we can start moving towards alternative energies, renewable energy sources, carbon capture technologies, etc. Especially for you, some of my younger students who can't vote yet, it's even more important that you make your voice heard to ensure that the ideas and the truth that you know and that you speak actually can get represented in terms of the legislative changes made by our democracy. At the end of the day, though, you might hear lots of criticisms of climate change. We've talked about these at points throughout the year. You might hear something like, well, what if we do all that stuff and it turns out climate change wasn't a big deal? What if the science is wrong? Well, to that, I simply say, well, then we would have made the world a better place regardless. Perhaps that's naive of me, but I think in a situation where it's very much do or die, we don't really have any choice other than to be optimistic. And the best case scenario is that climate change isn't a threat, and we did all that stuff, and we switched to renewable energy, and the air pollution has gone down, and we don't have to worry about non-renewable resources, and the world's a better place, and it's more equitable, and everybody has access to electricity and food and water. And the worst case scenario, climate change is a serious threat, and you know what? We took every step we could to prevent it. So at the end of the day, that's where I stand. I think it's almost mandatory that we do everything we can to combat climate change. And that's all I got for you today. So if you've got questions, let me know, and I'll see you next time.